Okay, good morning. So, I'm Christopher. This is joint work with my former PhD supervisors, Delaram and Siamak, and my current boss, Ludovic. And I guess, so, I mean, the title of this makes you, I'm kind of assuming there's two camps here. There's people who think, what is SDLP? And there's another camp that says, didn't I see some stuff on ePrint that said this was polynomial now? So I kind of have answers for both of you. So yeah, there has been some work recently that talks about reduction to these like quantum easy problems that works in finite groups, but not for semi-groups. In this work, I'm going to talk about a reduction to a less quantum easy problem, the difficulty of which is, I guess, somewhat disputed. And in this, it's more general, basically. So we're talking about finite semigroups here, and I will be making definitions as such. And here's maybe you can understand why this has happened, right? So this is a bit of a timeline of the area. So I guess stuff moved quickly. And so you can see that this recent like polynomial time stuff is rather recent. All right. So we got ahead of the scandal. Let's get onto this. So SDLP, which stands for the semidirect discrete logarithm problem. In order to define it, I first have to define the semidirect product. This is defined for groups generally, but as I said, I'm in semigroup land today. So let G be a finite semigroup, and we consider the semigroup of its endomorphisms. We can take pairs of semigroup elements and endomorphisms and define a multiplication that looks like this. We get something that's called the semidirect product group. And if we're interested in what happens if we take exponents in this semidirect product group. So if we keep carrying out repeated multiplications, we're going to get stuff that looks like this, right? So just using the fact that phi is an endomorphism, I'm going to preserve my multiplication. And in the first component of this multiplication, I'm going to get weird looking products where I going to take increasing powers of this endomorphism and then add it to this long product. And this is kind of going to define our problem instance. So to avoid having to write all that down every time, I'm going to define this function S that goes from the natural numbers into the semigroup. And it's defined with respect to a choice of like basis pair here. So I fix this G phi to start with. That gives me a function S that goes from the natural numbers into this semigroup. And I just define this S of X to be exactly what happens when I compute this exponentiation and then project down onto the first coordinate. And we've seen in this previous slide that S of X has this form, right? So SDLP is defined as you might expect. It's this analog of the discrete logarithm problem. We say, all right, let's fix this pair G phi, and we'll say we're given S of X for some integer X. Our task is to recover X. It's a generalization of the discrete logarithm problem in the sense that you can see that if phi is just the identity, then we're going to get the regular discrete logarithm problem back. Okay. I'm actually not sure how useful this is, but let's look at a little example, maybe. So if we take G to be this like matrix semigroup, so just not everything's invertible, and an endomorphism, which in this case is an automorphism defined by conjugation, then if we keep sort of computing these products, we're going to get products that look like this. The point I want to make here is that if we keep going and we get to S of 10, it turns out that S of 10 is equal to S of 2. So that kind of suggests that there's some looping behavior going on with this structure. Might imply some periodicity, quantum techniques. And actually what it also implies is a group action. So basically what we do here is show that we draw a connection from this SDLP to a group action, and then that gives us access to a bunch of techniques that we can synthesize. So let's see why we get this group action. The first thing to note is that we have this like star operator, which I will be using a lot, and kind of just following through a bunch of definitions, the point is that this thing here is the same as this thing here. So you can see that we've kind of extracted one of the arguments of S from this function, right? So this is S of X plus Y, but here I was able to compute S of X plus Y by, I've kind of separated X and Y out. So the point is that we can add in the argument of S. Like if we're given S of Y, we don't know what Y is, we can compute S of Y plus any integer without having to compute what Y is. So we have this like partial homomorphicity. And I will use that to define this function star, which goes from, it kind of takes pairs in the natural numbers and curly X and maps these pairs to something else in curly X, just using that we can use this star operator to add in the argument of S. I mean, we heard a lot about group actions yesterday, and this already is looking suspiciously like one. For those of you who weren't at the group action session or maybe forgot, let's remind ourselves what a group action is. Okay, I got my slides out of order. Here's a group action. Remember that we got this group and a set and a function, and we take pairs in the group and the set into the set in such a way that the identity fixes everything, and everything, the group operation and the group action, like play together nicely. And we have this problem that we heard about as I can't remember what people called it yesterday. It goes by many names. I'm using generally the one introduced by Kuvenia, which is calling it the vectorization problem. And it's, again, this like generalization of the group action discrete logarithm. It's this generalization of the regular discrete logarithm problem because you can define taking discrete logs as a group action if you like. So you're given a pair in a set and you have to find a group element that maps, that kind of takes one of these set elements to the other if one exists. All right. So remembering that we defined this curly X to be, all right, we got this function S, remember that takes us from the natural numbers into the semigroup, and we can add in the argument of S. So we can compute compute 1 star S of 1, that's going to give me S of 2, and so on. So I can like use this graph to define, I can draw this picture using these graphical methods of the whole of curly X, right? And the thing to notice is that, well, curly X is contained in a finite semigroup, so it must also be finite. In other words, this diagram has to start looping back around eventually, because otherwise we'd be generating infinitely many elements of curly X, which of course we can't do. So let's let this little n be the first place that this starts happening, and r be the number of steps we have to take before we get back here. So I guess a couple of things to notice here. Well, this diagram's kind of quite cleanly divided into two parts, right? We've got this like non-looping part where there's not a lot of structure, and then eventually we start getting some structure back. So remembering before that example I showed you, we started looping back to 2, right, not to 1. So we had a tail in that case as well. And another thing to notice is that once I'm here, like if I take r steps around this loop, I'm going to be back where I started. So another way of thinking about that is that if I take r acting on some node in this loop, that's basically like doing nothing, right? Because it's just going once around the circle. And similarly, I can also go twice around the circle and end up in the same place. So that kind of implies that we're interested in star with respect to like residues mod r. So I'll introduce a little bit of terminology, which is pretty standard from like monogenic semigroups, if you know them. So this little n where we start looping is called the index. The length of the loop we do is called the period. This like blue nodes unstructured bit is called the tail. And the bit where we start having some structure is called the cycle. So there's the loop, the cycle, whatever. So I guess we can talk about what we showed. So I mean, as I hope I've intuitively argued, it turns out that this loop structure is indeed a group action. So remembering that R is the how long, how many times around this circle you have to go to end up in the same place, or the length of the circle, I guess. It turns out that this group of residues mod are this loop that I showed in the picture before, and something that's basically just star, but I'm writing it differently to show that I'm now accepting arguments that are all residue classes rather than just integers. It turns out that that's a free transitive group action. And free and transitive for these purposes means that this vectorization problem that I talked about will have not only a solution, but will have a unique solution. So that's considered a good thing, I guess. I'd like to talk a little bit more about this second contribution we get out, which is, okay, so I can use this fact that we have a group action to show that there's a reduction from SDLP. Well, I get this subexponential quantum algorithm out, is my claim, and I'll talk a bit more about this now. Okay. So yeah, let's talk about the reduction. Maybe I can give a little bit of background first. So it's known, or has been known for a while, that this vectorization problem in a commutative group action, I should have written that, you need your group to be commutative, reduces to this, it reduces to something called the abelian hidden shift problem, which in turn can be solved by Kuperberg's algorithm for the dihedral hidden subgroup problem. There's improvements to this due to Regev and so on, and I think Kuperberg again. But I mean, this is like the famous number. So basically, if I can show, because of previous work in the literature, if I can show that I can use a vectorization problem oracle to solve SDLP, I'm done. Right? Like I have my claim of a sub-exponential complexity attack. And in order to argue that I do indeed have this reduction, I'm going to use some techniques developed by Childs and Avanios, which when they were interested in the classical semigroup DLP, they encountered structures that had quite a similar shape. So I can use some of their arguments or use some of their techniques. So I mean, first I'd like to kind of point out that this reduction isn't necessarily straightforward, right? Because there's two scenarios. Remember I'm given S of X and I have to find with respect to this pair G phi, and I have to find this integer X. Well, there's two scenarios we could be in. X could be less than N, where we start looping, in which case we're in the tail, and our vectorization problem, because our group action only happens in this bit, our vectorization problem oracle isn't really going to tell us anything. So there's not an obvious reduction there. And similarly, even if this challenge value we've been given is in the group action part, okay, I can find out how to get from here to here with a call to my vectorization problem oracle, but I've still got this weird tail to address somehow. So I claim that it suffices to know these values N and R. So remember that N is where we start looping and R is how many times, how long the loop is. So if I know them, well, first of all, I have a way of checking if I'm in the cycle or not, right? Because I only start looping at N. So it only makes sense to go around the circle once if I'm already on the circle. So I can if I know R, I can already check if I'm in the cycle or not. So this is the procedure I'll do. So first I'll do that check. I'll check if I'm in the cycle. If I am, well, I can just do this vectorization problem oracle. So remember we're in this scenario. And then I know N, so I can just add that on. Otherwise, I can just so I can keep projecting myself forward from this point. And eventually, just by binary search, I'll find the smallest integer that gets fixed such that this new point I'm on gets fixed by R, right? So we're not, in this case, using we're not using a call to the vectorization problem oracle, but we have binary search techniques, so it's kind of efficient anyway. Okay, and none of that's going to be more expensive than the complexity implied by Kuperberg's algorithm. So we're done, provided we know N and R. and we can compute n and r as well, right? So first of all, if we know r, we can compute n just like by similar techniques. It's going to be the smallest. We're just doing some binary search procedure to find the smallest integer that gets fixed under r. And so we have like a sort of Shor-like method of finding r, right? So like in Shor's algorithm, we prepare a state that looks like this, and we can understand the like procedure that we take to be observing the second register. There's a chance that this fails because we might observe the second register and get something in the tail, in which case we don't learn anything. But this has like some constant probability of failure. Otherwise, we get, just by like these interference laws, if we observe something in the cycle, then we're going to get all the integers that get projected to the same place in the cycle by this function s. And this is exactly the kind of state that we see in Shor's algorithm, and we can do the standard QFT continued fraction tricks that give us back the period. So because we have to deal with this tail, we like incur some slightly worse polynomial exponent, but it's basically just Shor's algorithm. And yeah, I guess to sum up, because we have Shor's algorithm to find r, we can find n. And then because we have n and r, I argued that meant that we can solve SDLP with a call to a vectorization problem oracle, which has sub-exponential time. So we're done. Fin. So yeah, we can solve SDLP for g phi in quantum time with this like parameter r that depends on g and phi. I guess we don't know much about its size in the general case, other than it's got to be less than the size of the semigroup. In the generic semi-groupy case, this remains best known, although, of course, as I talked about at the start, if you want to specialize to some choices of finite group, you can do much better. I would be interested to know if there's some like specialized choices of finite semigroup that you can do better in, for example. Because also, if you can compute these values n and r classically, you do have an effective group action, effectively, right? Because you know how to sample and stuff, because you know r. Although, of course, that might succumb to similar, I don't know. I mean, you might get nice crypto out of it, maybe. I don't know. Something to check. If you'd like to know more about, this is kind of an example of the not very well studied field of group-based cryptography, I guess. And I've got some recommended reading for you. So we actually very recently got the big result. We showed that actually SDLP is easy in all finite groups, so we don't have to like take a specific choice of finite group. So that was a paper that was made possible by the organization of an American Institute of Mathematics workshop a couple of months ago. And there's some like write-up of what people are interested in group-based cryptography if you wanted to read about that. And that is everything that I wanted to say.
Thank you, Chris. Any quick questions? Because we run out of the time. Yeah.
Hi, thank you for the lovely talk. You had the slide where you mentioned briefly Shor's algorithm and this possible failure. Yeah, this one. So this possible failure is somehow related to the relative size of the tail and the loop, I suppose. And you alluded to this also later, but the efficiency or effectiveness of this reduction is also to do with this parameter r. Is it really the case that we know basically nothing about the size of r for general endomorphisms, or?
I mean, I don't know anything about it. It wouldn't surprise me if you could get some like tighter bounds on it that depended on the choice of. But I mean, I guess in a very general context where, I mean, because these like arguments you're making are almost like purely symbolic, like there's not a huge amount that you can do a priori. Yeah, I suspect you can. I mean, it'll have some interactions with like the normal size of monogenic semigroups when you're just taking like standard exponentiation. But I also think that in the general case, not a huge amount is known about the sizes there either. So there's probably work to be done there, but yeah, I don't really know much about them.
And excuse the naive question, but when maybe trying to build crypto from this kind of thing, do you envisage a semi-group being fixed and the selection of the endomorphism being part of some kind of key generation, or would you also fix the endomorphism? Or
I guess you'd fix a choice of, yeah, I think you probably have to fix both, and then the key generation would be like working out what these two parameters that define the like shape of the resulting structure are.
right?
Although again, like whether the choice of like good pairs is sort of homogeneous across all pairs, I mean, you'd think probably not, right? You think there'd be good and bad choices.
Yeah, any worst case to average case reductions in the pipeline?
No, I'm
Okay.
afraid not. It'd be nice though, wouldn't it?
Thank you very much. Lovely talk.
Any more questions? All right, let's thank Christopher again.